Okay, so this is the second video for momentum in Forces 2. So here we're looking at conservation of momentum. So the total momentum of a system, all objects, is always conserved. Okay, so in all these collisions here, the total momentum is conserved. So let's say we're looking at this first one. This one's coming in with some sort of momentum, crashes into this one which has no momentum. Then afterwards, the total momentum is still going to be P. In this case, this one has P, and this one has negative P because it is a vector. Okay, so momentum is a vector, the direction is important, and because we're going, instead of going right, which is positive, we're going left, which is negative. Okay, so right is positive and left negative. So if we change direction, we change the sign. Okay, so this case, what's the total momentum? It will be P plus negative P. Okay, so if they're the same size, the total momentum on the left here will be 0. And then on the right-hand side, this negative P of that one now, added to the P of that one, must be the same. So total momentum before of those two added together must be the same as the total momentum of those two afterwards. So that means conserved. The total value of momentum before is always going to be equal to the total value of momentum afterwards. And to find the total value, you always add up the different objects. So here's an example for a crash. Total momentum before equals total momentum after. Okay, so let's say we had a car going along with a certain velocity. Let's say it's got a velocity of 10 meters per second, has a mass of 10 kgs. This has a momentum of 10 times 10, which is 100 newton seconds. Okay. Now this is going to come in and crash into a car that is stopped, 0 meters per second. And 0 times anything gives you a momentum of 0. Now, when they crash, this total momentum of 100 plus 0, this 100, stays the same. So that value of 100 newton seconds stays the same after the crash. So let's say afterwards, this car here now heads off at a certain speed. Let's say it was, and this thing was 5 kgs, it head off at 20 meters per second. Okay, and then the other one will be stopped. Okay, so the 10 kg guy, this one's 5 kgs. Sorry, pen doesn't really like small writing. So this one's 10 kgs, the other one's 5 kgs. This one has a 0 meters per second, and the other one is 20 meters per second. Now, let's see if the momentum is conserved. So 0 is the momentum of this one, and we're adding it to this one, which will be 20 times 5, and that will be equal to 100 newton seconds. And they're both positive. Okay, so in this case, the momentum is the same before and after, so momentum is conserved. And this then just sort of expands all that. Okay, so total momentum before equals total momentum after. You add up all the momentums of the different objects before and after, and this is how you calculate the different momentums before and after. So it's just the same thing, just expanded. Now let's say we have some other examples. Let's use the green pen again. So this time we have a car travelling in 10 kgs, or a cart, okay, 10 kg car is pretty light, at 10 meters per second, and another cart is heading back the other way at let's say 20 meters per second, and it's a mass of, let's say, 10 kgs. Now, so total momentum before is going to be the momentum of this one plus the momentum of that one. So the momentum of this one is going to be mass times velocity, so mass times velocity equals 100. This one's going to be negative 20 because it's going to the left, times 10, and so that equals negative 200. So what is these two added together? 100 plus minus 200 equals minus 100. So that is my total momentum before. Okay, so what happens afterwards? Let's have a look. So we've got this from before, and now afterwards the cars are going to crash and move away. Okay, so this one here, this 10 kg, is going to go to the left now. So this one could go to the left, let's say at 6 meters per second. I'm making this up, so in reality it's probably not true, especially if we look at energy. Okay, but this is just for momentum. We're just showing you the equations. So this first one here is now going left at 6 meters per second and it's 10 kgs. Now the other one is also going left, so they bounced off each other, they crashed here, and then one's going this way, and the other one's going the same way, but at a slower rate. Okay, so the other one might be going at 4 meters per second, and it's also got a mass of 10 kgs. Now, if we work this out, the total momentum afterwards, so the momentum of this one plus the momentum of that one must equal 100. Okay, let's see if it's true. So, momentum of the first one will be 6 times 10, which equals 60. The other one's going to be 4 times 10, which equals 40. So, total momentum added together will be being aware that these are negatives now, the speeds, and also momentums is going to be negative 60 plus negative 40, which equals negative 100 Newton seconds. So yes, momentum is conserved in this case. Okay, let's say we had this thing here, which we'll call a bomb. Now, when this thing explodes, it's going to separate. Okay, now we can use momentum to see what's going to happen. As the pieces fly out, the conservation of momentum will still apply. Okay, so we've got some pieces flying out all over the place. Now what we could do is say, well, what's the total momentum beforehand? Well, this thing is at rest. Okay, so the total momentum beforehand is 0. And that means when I add all these things together, when it's exploded, they must all add to 0. And it could happen, especially if we're only looking in 2 dimensions. So let's say we had our object like this, and it's going to be split down the middle. One part's going to go that way, one part's that way. Okay, so nice and easy, just left and right when it explodes. So beforehand we have 0, afterwards this one, so this object plus this object, let's try and draw the halves. That one, let's call it B, and this one A. A plus B must also be equal to 0 afterwards. So let's say this whole thing had a mass of 50 kgs. Beforehand, the velocity equals 0, so then the momentum is 0. Mass times velocity equals 0. Afterwards, this one here has, let's say, a mass of 20 kgs, and this one has a mass of 30 kgs. We haven't lost any mass in this explosion. This one's got a velocity to the right of, let's say, 10 meters per second, and then this one's got a velocity of, don't know. what is that velocity? Okay, so afterwards the total momentum has to be 0. So the momentum of this one, 30 times we don't know, and we're going to make it a negative don't know, plus 20 times 10 equals 0. Okay, so let's say we move 1 to the other side. So we get equal sign there. 20 times 10 is equal to 200. Move it to the other side. We're going to get negative 200. And that means we've got 30 times something equals negative 200. Okay. And so how do we work that out? Well, we just say that this is your, you could look at a triangle, we won't do that. We could work it out by saying that our velocity we don't know will be equal to how many times 30 goes into 200. Okay, in this case our velocity is going to be 6.67 meters per second. And it'll be a negative because it's to the left.